Hello, everyone. Welcome to my home. This is my guest bedroom here behind me, um, and I. This is our first real, honest to God, full lecture here for Psych 300 since we've all been sent home. So I hope that the test went well for you. I hope that you liked your results. The results were generally significantly better than usual. For a stats test, but you know what? I think that's just something we're all going to have to live with, isn't it? So here in our next chapter, the book calls it Beyond the Null, but I prefer to call it Why Did Marie Almost Have a Stroke and Die in Statistics Class? So here's the deal. Displayed here in front of you on the title slide is one of the I don't like to use the word favorite, but one of the classic students that I've ever had, um, Marie. She was the president of Psychology Club, the president of Psyc, organized a whole lot of pub crawls for us in Canada, and she was taking my stats class at one point early on in my career. And the story goes that she got up as we were discussing statistical power at one point during one of the classes, kind of walked out into the hallway. And like usual, I didn't really necessarily notice. I mean, people come, people go, they have to go to the bathroom, they have their own things. I don't judge. And so I just don't really, I really go out of my way not to even notice. But I didn't notice that she got up and I didn't notice that she hadn't come back. And so it wasn't until after class that somebody went down and found her. We had a lounge for the um, psychology club in the psych building, and there she was on the couch. She's like, I don't feel so great, and people started to really worry what was wrong and called an ambulance and navigated through the building, which was quite confusing, um, until they got to her and they said, sweetie, what's going on? What did you take? Which was really kind of an insult because they assumed that somebody who was having the kind of disorientation and dysfunction that she was having from a person of her age must have been overdosing on a drug of some sort. Not the case. It turns out Marie was in the middle of having a full left hemisphere hemorrhagic stroke, which is a hemorrhage in the brain, a lot like an aneurysm, but not quite. It's kind of in the middle. I don't understand all the terminology. But basically, by the time that vascular event was done, the entirety of her left hemisphere was kind of soaked in the blood that had leaked out of her blood vessels that afternoon, which is a really bad position for a person to be in. So we all, a few other students and me, we were waiting in the waiting room. We were looking for updates. They transferred her to another hospital. We were kind of sure that we weren't going to actually ever see her again. She was in an induced coma. But the good news is that she made it. She made it through, recovered in a way that surprised a lot of people who predicted more language and others and spatial deficits for her, but ended up recovering, going back to school, getting her degree, getting married, and as you saw in the last slide, having a kid who is about maybe 7 months old now. So things got back to normal. It was pretty cool. But usually about the time that we start with power, I check in again with Marie and say, do you have anything new to say to our people as they begin statistical power? And recently Marie said, this year I wish this year's tribute's the best of luck. Remember, headache isn't always just a headache. Most of the times it is. Sometimes it's a hemorrhagic stroke. So power, be careful with it. This topic is tough. This topic makes you think. This topic is a little bit hard to get your head around. The math is not difficult. In fact, there's less math here than there is in our typical chapter. But the concepts have a tendency to really give people a run for their money and twist their brains around a little bit. And so it's important that you pay special attention to the logic of what is going on here and follow along and really make sure that you understand every step by step. Because Marie isn't the end of the story. When we were doing an in-class assignment on power, the first year I was here at CNU, Another student passed out in the middle of the class, and we called the ambulance, and the ambulance came to Forbes in a very confusing building and finally said, "Hey, how are you doing? What's going on? What did you take?" And she said, "Nothing." Well, what she hadn't done was eat for the whole day after having given blood at the blood drive um, over at the Ferguson Center. So, but still, man, statistical power strikes again. So drink a lot of water, take care of yourself, be careful, make sure that you're feeling well when you take on this stuff. So what I want to do is go back to where we had been when it came to hypothesis testing before we give it a little bit of a twist. A review on what has gone on in the logic of hypothesis testing so far is this. Hypothesis testing throughout the entire procedure always assumes that you are working with the assumptions that are true under the null hypothesis. What that means is you assume that there's no difference, that what you're looking for, you're assuming the difference you're looking for isn't there. You assume that group 1 is exactly equal to group 2, or that everybody's exactly the same before as they are after. And then you compare your results to that assumption. If your results were somewhere in the middle here, which is to say, a relatively likely event to have happened if the null assumptions were true, that is right in here, okay, then in that case, you go ahead and you accept the null hypothesis, which is to say, yeah, the two groups were the same, or people were just the same before and after, but it's only when you get a result that was on the edges here, in the fringes, that you say, these results were so unlikely given the null assumptions that I'm going to actually assume the null assumptions were false. Okay, so likely values here in the distribution of results that you would get if the null hypothesis was true would let you assume that the null hypothesis is in fact true. Okay, and that happens for results that are anywhere here to here. All right. Now, the other thing is, if you get a result that is outside of that, either this way or this way, then what you have is a conclusion that the null hypothesis was false. You got a result that was so unlikely given the null assumptions that the null hypothesis was false. And that's where we have always stopped. That's where it ends. You either say, I endorse the null hypothesis, or I don't endorse the null hypothesis. But you never go on and say what is actually true. You just say, the null hypothesis, this statement that everything is exactly equal, is probably, or according to some criteria, probability false. All right. This chapter lets us do a little bit better. Okay? All right. So what we're going to do is give a little bit more information about what the not null population actually would look like. Instead of just saying, you see the null, it's not that. We can say a little bit about what this alternative to the null distribution or null assumptions would actually be. So starting with our traditional, what we've already done, null and alternative hypotheses, we'll start with that, and then we'll tell you some more ways you can describe what goes on when the null is false. So a traditional null hypothesis would be something like this. The basketball team is the same height as the overall CNU undergraduate population. And you would either accept that if you took a sample of basketball players and a sample of CNU students, compared their means, and didn't have a big enough difference relative to the error to declare with 95% certainty that they were from different populations, you'd say, yeah, that's a fine null. Everybody's the same height. Okay. That would mean that under these assumptions, in this case, the alternative hypothesis is that one of the groups is different. That includes either basketball players are taller than average or basketball players are shorter than average. Either one of them would be fine. As long as there's a difference between those two groups and it's big enough relative to the sampling error, you're going to reject that null hypothesis. But that seems a little absurd, because everybody knows that if you find a difference between the basketball team and the regular population, it's going to be in favor of the basketball team being taller, right? So why can't we make use of that? That would mean doing one of the new kinds of alternative hypotheses that we're talking about here. A new alternative hypothesis might be that the basketball team is taller on average. That's something we haven't done before. But if your hypothesis is that the basketball team is taller on average, you are willing to declare that you're wrong in this prediction if everybody's the same height, or if it turns out that the basketball team is shorter. Both of those are possibilities that you get to say, nah, it wasn't right, okay? Another alternative hypothesis is very, very specific. Say, I predict that we will get results that are in line with the idea that the basketball team is, say, 3 inches taller than on average than the other people in the population. So you make a specific prediction about a specific amount of difference. And that's going to turn out to be very important when we start talking about this concept called statistical power. Let me give you some examples of what's going on here. When we do specific predictions like that, we can do directional hypotheses. When we start saying that one group is predicted to be taller, or one group is shorter, or one group is less than, or one group is greater than, what we're making is called a one-tailed hypothesis. We are only going to entertain the possibility of success if things go in the direction that we predicted. We'll tell you why that's called a one-tailed versus two-tailed test. The next thing we're going to get to talk about is this idea of treatment effects or effects. What is the actual size of the difference between one group and another, one condition or another, or one treatment or another? And that's in the last slide by saying, like, the effect of being on the basketball team is that you are on average 3 inches taller. All right. So when we have a treatment effect discussion, we start talking about exactly how big the size of the difference was between two groups. Okay, so that's interesting as well. And that will let us do this whole talk about what's called power. Power is the probability that we would get a statistically significant hypothesis test if an effect of a certain size was actually real. That gets pretty hairy. We'll leave that for a little bit, but let's start off with one-tailed and two-tailed tests. Okay? All right. So alternative hypotheses, including one and two-tailed tests, will look a little bit like this. All right. An alternative hypothesis is and always will be, and is under all circumstances, any hypothesis that is not the null. That is to say, any hypothesis that doesn't include an expression of equality. I've told you that the null is an expression of equality. Well, the null can be an expression of equality and some other possibility, but whichever prediction involves everything being equal will be the null hypothesis. So, traditionally, our alternative, or otherwise known as research hypothesis, has been that the null is false, but I don't care which direction. So traditional null would be that there is no difference between the amount of candy, say, that girls and boys eat on Halloween. All right, here are two random children. Here's one dressed in a bluish outfit. Here's another one dressed in a bluish and greenish outfit. I've never met them. They're strangers to me. They're totally not my children. Okay. Okay, and here is the alternative hypothesis under the old way of doing things, the things that we've been doing so far, which is that whatever direction this result goes in, we don't care. It's non-directional. So if it trails off into the tail of the distribution that indicates that boys eat more candy or collect more candy than girls, that's fine. If our results are so far in the direction of girls collecting more candy than boys, that's also fine. Both of them make a statement of equality false. All right. But let's say that due to a lot of previous research, a lot of investigation, a lot of empirical data that's been gathered, I really think that girls are going to end up collecting more candy on Halloween than boys. So my new research hypothesis is going to be, if there's a successful study done here, it's going to result in girls having more candy than boys. So that's my hypothesis. Girls greater than boys. That leaves everything else that could possibly have happened in this study to be the other hypothesis. All right? That means that if they are equal, or if boys eat more than girls, then I'm wrong. And if I'm wrong, then what I'm doing is endorsing the null hypothesis. I'm calling the null hypothesis true. All right? So the reason that it's the null is because it still includes that statement of no difference. If they're both equal to each other, well, the null is true, but now the null has a little bit more inclusivity, a little bit more baggage. If they're equal or if boys have more, then the null is going to be true. But only if girls outpace boys will my prediction end up being true, and my alternative hypothesis will get endorsed. All right, couple of rules for making these hypotheses. Between the null and the alternative hypothesis, all possibilities that you could possibly get for your study have got to be covered. Everything from the infinitely improbable in one direction to the infinitely improbable in the other direction have to fit under your design in a way that you would be able to assign a conclusion to every result that you could possibly get, right? So the alternative saying that girls eat more than boys has got to cover, the alternative to that has got to cover equality and boys eating more than girls, which is why it is called one tail. What that means is, if you can look down here in the chart, all of the possibilities that are included in us being right fall on one tail of the normal or t distribution. Everything else in the other tail is now a part of the null distribution where we have to say we failed. Okay, so everything here in one tail, that's why it's called a one-tail test, otherwise known as a directional test. Any result that you get that falls into the white area means you accept the null, and only those values that you get in the red area now are ones that you get to use to say that you reject the null, or you were right, you accept your alternative hypothesis. That only allows you to reject the null if things are in the right direction. So what's the point? Why wouldn't I want to give myself a really good chance to be right just in case things go in the other direction? Have I thrown away some possibility of being right, which would have been really nice? Why have I done this? Is there any advantage to it? The answer is actually yes. There is a big advantage in moving around the probability that you'll get to say you were right versus you'll get to have to say that you were wrong when you do a one-tailed test, which is this. The critical value moves and it becomes easier to overcome. It becomes less stringent. It becomes less conservative as you move from a two-tailed test to a one-tailed test. Here's why that happens. Right now, this is a two-tailed test with an alpha of 0.05, which means that half of the alpha is over here on the left and half of the alpha is over here on the right. But if you do a one-tailed test and you keep your alpha, you actually get to put all of the alpha in one direction. So instead of being 2.5% on the left and 2.5% on the right, now the entirety of the possibilities that you're entertaining for making this hypothesis test statistically significant are all on one side of the distribution. That makes that area twice as big. And so you've got to move the critical value in towards the mean to accommodate that that tail is basically twice as full or twice as fat. Here's how it ends up working. You take all of the area away from the left and you put it on the right. Well, now it can't all fit into an area marked by your old criteria value, your old critical value. So you've got to take that critical value and move it to reflect how far out you have to go to reach the last, not 2.5% anymore, but the last 5%, the last 0.05, which is now all in the same direction. Now realize that the disadvantage is that it doesn't matter how far you go to the left, you're never going to reach significance. But if, as long as you're going to the right, now you don't have to go as far as you used to in order to declare statistical significance. This could end up being a big deal for you. All right, so let's run an example before we're all done. I lied. These are my children. I took a video, this is like 5 years ago, of Maria dressing up like Pablo from the Backyardigans, a fabulous children's show. If you ever have children and it's still hanging out anywhere on the interwebs, I recommend Backyardigans. It's one of those things that adults can actually watch, and the music was fabulous. Anyway, So let's say here's a mock data set. I took a sample of 11 boys over here on the left. They averaged collection of 66.45 pieces of candy. They are group 1. Therefore, their data all has a sub 1 to it, and the average sub 1, 11 boys, is 66.45 pieces of candy. Sub 2, girls group, had 11 girls as well, and they averaged 74.95 pieces of candy. Right? So X bar sub 2, which is to say the average number of pieces of candy from girls is 74.95. Now again, these are both statistics. These are not their populations. This is just 11 data points from the boy population and 11 data points from the girl population, doing their best to give you a close approximation of the mu in those populations. Instead of making you do all that math and doing all that stupid stuff, I am just throwing you the standard error for the difference between those two means. It is 4.42. So this is an independent samples t-test. The standard error for the independent samples t-test is 4.42, and the statistic for analysis is X bar sub 1 minus X bar sub 2. That is to say the difference between the boy and girl samples. I'm going to use an alpha of 0.05. Okay? Now, the two-tailed test would look like this. These are our old familiar hypothesis test statements of the null and alternative hypotheses. The alternative hypothesis is that the population of boys is not equal to the population of girls. Alternatively, also, you could say that if you subtracted those two populations from each other, you get a value that was not 0, something big or something less. The null hypothesis is that they are equal, and or if you subtracted the two of them, you'd get 0. The critical value, we can do that using degrees of freedom. There were 11 people in the first group, 11 people in the second group, minus 2 gives us a degrees of freedom of 20. And we would look up an alpha of 0.05 from our handy dandy t-table that you've already been working with in Appendix B at the back of your book, and you get a plus or minus 2.086. That means as long as those two means, the mean of girls and the mean of boys, was more than 2.086 standard errors apart, you're going to declare statistical significance. Let's see what happens. The statistic for analysis here is the mean of boys minus the mean of girls divided by the standard error that I gave you for free in the last slide. That's a negative 0.85 divided by 4.42 is a negative 1.92. All right, so our test ratio is negative 1.92. Boys fell 1.92 standard errors below girls. The difference between those two means was 1.92 standard errors. The question is that a lot? Is that enough? And when you compare the test ratio to the critical value, you realize it is not. You needed to have those two statistics, X bar 1 and X bar 2, 2.086 standard errors apart in order to declare statistical significance. We weren't there. So since we didn't achieve a big enough test ratio to overcome the critical value, we've got to settle for the idea that our answer was kind of in the middle and it is not good enough evidence to declare statistical significance. We accept the null, we say everything's the same, and we fail to reject. Now, let's map out what that looked like visually, because this is where it's going to be easiest to understand the change that's coming. We were going to reject the null hypothesis if we got results that were either so far to the left in the left red area or so far to the right in the right area that we could reject the middle. We got a result that was right here. Almost 2 standard errors below the middle of that curve, which is close, but it's still considered a middle value, a value in the middle, a value that's kind of expected if the boys and the girls didn't collect different amounts of candy. And so it didn't cause us to reject the null hypothesis. We were not quite far enough away from the middle to get into the region of rejection there on the left. All right. Now let's run everything in such a way that the statistic for analysis is the same, the sample size is the same, the sample standard deviations are the same, the standard error is the same, alpha is the same. We're actually using the exact same data set. Nothing is different. Except now we're going to start with a one-tailed test, a directional test, instead of a two-tailed test. We are going to expect that girls eat more candy. So here is what our alternative and null hypotheses look like now. We expect the mu of boys to be less than the mu of girls. Alternatively stated, if you subtract the mu of girls from the mu of boys, you'll get a number that's less than 0. So we're not going to be excited by any positive statistics for analysis here. They've got to be negative. And not only do they have to be negative, they have to be negative enough. Here's the null hypothesis. Either boys and girls are exactly the same, or boys end up eating more than girls. Another way of stating this is that if you subtracted girls from boys, you would get a number that was equal to or greater than 0. All right? That's how you write that down. Everything else is the same. The degrees of freedom are the same. Oh, but here's where we run into the actual math difference between these two designs. Appendix B, the T-table that I've been giving you to work with tests this whole time, has had in the heading, in a place that you may never have noticed it, a distribution of T two-tailed. It's never been an issue before. You've never had to look at it. You've never had to consider it. But that was only one possibility. That table only covered the possibility that you were doing a two-tailed test. There was an entirely different T-table for when you do a one-tailed test, and that is Appendix C. At the top, it will say distribution of T one-tailed. You calculate the degrees of freedom the same, you do everything the same, except that this table is going to give you a slightly different critical value than the last T-table. So again, all of the math gets rolled into using the right table, and that changes your critical values appropriately to accommodate what you're doing. All right. So alpha equals 0.05, you put it into the table, you look down 20 degrees of freedom, and now, instead of needing a plus or minus 2.086 in the one-tailed test table, you only need a negative 1.725 in order to achieve statistical significance. That's where the difference comes in. The test ratio, it's the same. Since our x bar sub 1 and our x bar sub 2 and our standard error were all still the same, we still have boys being 1.92 standard errors below girls. But when it comes time to evaluate whether we have statistical significance, everything is going to change. In a two-tailed test, we don't have significance. We've got a value there that's in the middle. But under a one-tailed test, when we take all the red area from the right and we make the left tail full up to 5% instead of just full up to 2.5%, we realize that we've expanded the region of rejection. We've expanded the critical region to the point where now it does envelop, it encompasses, it includes the results of our study. So now under a one-tailed test assumption, we get to say, we're at least 95% sure that girls do eat more than boys or collect more candy than boys on Halloween, right? So that's kind of a weird trick that you can pull. You can still say you're 95% sure, but if you were convinced that you were going to be 95% sure in one direction, you can actually lower the bar for yourself a little bit so that it's easier to get over. Before we get onto this, I think we've been at this for a little bit of a long time. I think it's time to take a little bit of a break. And I'm going to go ahead and give you a real treat. This is a compilation of relatively short bits from Mitch Hedberg. I mean, you've got to know who Mitch Hedberg is. You've got to know Mitch Hedberg. And if you don't, this is probably more important than stats for you. Mitch unfortunately died in 2005. Oh yeah, good job, Niehaus. Way to go. Just ruin it before it even gets started. But we still have him around. He lives forever on the internet, forever in our hearts. And in this time of national quarantine, it's kind of interesting to take a look at somebody who looks for all the world like he would like to be in quarantine, alone all the time, but nevertheless is compelled to get out and entertain. So, Mitch Hedberg, everyone.
I like rice. Rice is great when you're hungry and you want 2,000 of something. All right. Yeah. My mom loves those applause breaks. Refried beans. I like refried beans. That's why I want to try fried beans, because maybe they're just as good and we're wasting time. I went to a pizzeria. I ordered a slice of pizza. The dude gave me the smallest slice possible. If the pizza was a pie chart for what people would do if they found $1 million, this dude gave me the donate to charity slice. I would like to exchange this for the keep it. I tried to walk into Target, but I missed. I think the entrance to Target should have people splattered all around. I was walking by a dry cleaner at 3 a.m. and the sign said, "Sorry, we're closed." You don't have to be sorry. It's 3 a.m. and you're a dry cleaner. It would be ridiculous for me to expect you to be open. I'm not going to walk in at 10 and say, "Hey, man, I walked by at 3. You guys were closed. Somebody owes me an apology." I've been working. Hey, that's right. You guys did that for my mom. I find that Duck's opinion of me is very much influenced over whether or not I have bread. A duck loves bread, but he does not have the capability to buy a loaf. That's the biggest joke on the duck ever. Like if I worked at a convenience store and a duck came in and grabbed a loaf of bread with his beak and walked out, I let him go. I say, "Come back tomorrow, bring your friends." I bought a 2-bedroom house, but it's up to me how many bedrooms there are though, isn't it? This bedroom has an oven in it. This bedroom has a lot of people sitting around watching TV. This bedroom is AKA a hallway. This bedroom's over in that guy's house. Sir, you have one of my bedrooms. Stay out. If you're watching a parade, make sure you stand in one spot. Don't follow it. It never changes. And if you don't like the parade, run in the opposite direction. You will fast forward the parade. You know what, man? I got a parrot. The parrot talked, but it did not say "I'm hungry," so it died. I like sandwiches, but I hate sandwiches at New York delis. There's too much meat on the sandwich. It's like a cow with a cracker on either side. What would you like? A pastrami sandwich? Anything else? Yeah, a loaf of bread and some other people? I order the club sandwich all the time, and I'm not even a member, man. I don't know how I get away with it. I like my sandwiches with 3 pieces of bread. So do I. Well, let's form a club. I like to wear this pass because it helps me know when I'm upside down. This shirt is dry clean only, which means it's dirty. All right. Dry clean only, all right? All right, I'm ready to go. I had an apartment in Los Angeles, and I had a neighbor, and whenever he would knock on my wall, I knew he wanted me to turn my music down, and that made me angry because I like loud music. So when he knocked on the wall, I'd mess with his head. I'd say, "Go around." I cannot open the wall. I don't know if you have a doorknob on the other side, but over here there's nothing. I like Kit Kats unless I'm with 4 or more people. When I wear t-shirts, I can only wear V-necks because my neck is very fragile. I cannot wear a regular neck shirt. It hurts. And I especially hate turtlenecks. Like wearing a turtleneck is like being strangled by a really weak guy. All damn day. Like if you wear a turtleneck and a backpack, it's like a weak midget trying to bring you down. I thought my teeth were white until I washed my face with Noxzema. They are off-white. I'm not even white. I'm off-white. It's a new race. We will prevail. I saw a commercial on late night TV. It said, "Forget everything you know about slipcovers." So I did. And it was a load off my mind. Then the commercial tried to sell slipcovers, but I didn't know what the hell they were. You guys are cool, man. I wrote a script and I gave it to a guy who reads scripts, and he read it and he said he really likes it, but he thinks I need to rewrite it. I said, fuck that, I'll just make a copy. I went to the doctor, all he did was suck blood from my neck. Do not go see Dr. Acula. I like to take a toothpick and throw it in the forest and say, "You're home." I get up in the morning, I make myself a bowl of instant oatmeal, and then I don't do anything for an hour. Which makes me wonder why I need the instant oatmeal. I could get the regular oatmeal and feel productive.
I hope you enjoyed that. Now we're back. I have another person here on the slide. This is actually Lee Kirkpatrick. He is not a professional comedian. He is, in fact, a professional psychologist teaching at William and Mary. He's married to one of my friends from graduate school, actually, Brandy Burkett. Lee came to our graduate program in Santa Barbara a while back and said something that really made a lot of sense to me at the time, and I've been passing it on to my stats classes ever since. This is not something that comes from your book. This is something that I think is important, but that comes from me. When is it that it's appropriate to use a one-tailed test? Now, the book says if you have a reason to expect that your effect will be in one direction or the other, you can use a one-tailed test. I don't think we should. I think that this is not mathematically wrong, but it is sociologically a bad idea. And here's why. I'd like to illustrate Lee's point for him with the slides that I have coming up. Here's why you shouldn't use a one-tailed test. You should know how to do it. You should know the mechanics of it, but I don't think that you ought to ever do it. Here's why. One-tailed testing works like this, and it ought to be really, really hard to justify because just a hunch or just a prediction actually gives you way too much probability of making a type 1 error. It gives you too much alpha. It lets you lets you reject a true null hypothesis way more often than you ought to be rejecting a true null hypothesis, and here's why. If you are making a decision based on 0.05 and it's a two-tailed test, you have to go this far in this direction or this far in this direction in order to reject the null hypothesis. Okay, you know this. We've done this a whole bunch of times. This should not be new, controversial, or blowing your mind at all. But I'm going to run this in the context of a real world situation where a person who really, really wants to find a significant effect, whose career or whose dissertation might depend on finding something that they can get other people excited about, they can publish, that they can talk about. If you find a person in that situation and you give them the ability to play with a two-tailed versus one-tailed test, you might run into a situation like the one I'm describing. Let's say that you get a result, you get a statistic for analysis that is over here in the positive end, but falls just short of statistical significance in the positive direction. That is a huge bummer for you. You've wasted or spent weeks or months or perhaps years collecting a data set that you're really pretty convinced was real, but you just fell short of statistical significance. All right? If you find yourself in that situation, here's a thing that human beings will almost certainly be tempted to do. And it is this. You will be tempted to figure out, rationalize after the fact, some reason to justify a prediction that says, oh, I should have made a one-tailed test in that direction. Now that you know the data, nobody has necessarily seen your introduction. Nobody has seen your background research. You can tailor it, focus it, cherry pick it to make it look like you ought to have predicted a one-tailed test in that direction all along. And under those circumstances, you now get to expand the region of rejection in the direction you want, eliminate it in the direction that you know is fruitless for you, and give yourself a one-tailed test with alpha of 0.05. And you're like, that's no problem, right? I'm still an alpha of 0.05. Everything's good, it's fine. But here's the thing. Start over from the beginning. If you are a researcher and you really didn't, before the fact, have a strong reason to believe that the effect was going to be in one direction or the other, and you end up getting an effect that's almost significant, but in the negative direction, in the other direction, and you really want to publish and you really want to make sure that people take you seriously and that you need that dissertation or you need that promotion, well, it's not that hard to, again, go to the literature and have made a prediction that says, oh, of course it makes sense to say that the effect should have been in the negative direction. And so you, after the fact, go back and justify by cherry picking or focusing or arguing in another direction, and boom, suddenly you've justified a one-tailed test that includes this much area and includes your statistic for analysis in the negative direction. Given that it's almost always possible to, after the fact, after you've seen your data, justify making a one-tailed prediction in either one direction or the other direction, what you really end up with is a situation where you get to play with an alpha of 0.05 on the left and an alpha of 0.05 on the right, depending on where your data was, which means that at the end of the day, you've actually got now a two-tailed test with an alpha of 0.1. Any result that would have come in the most extreme 10% of your distribution is now something you can justify as statistically significant by playing around with which direction you want a one-tailed test to go. And there's no real way to keep people from that temptation. There's no real way to keep people honest. And so generally, as a society, as a science, we really ought to just kind of reject one-tailed tests altogether. They shouldn't be something that makes it into the psychological literature. That is my take. That is my opinion piece. That is my what I want to say, my op-ed. Okay, but I think there's a real reasoning to it. All right, so back to errors, hypothesis testing errors. We had talked about type 1 errors, but now we have to talk about type 2 errors. I remember telling you that the reason we call it type 1 is because there's also type 2, but I'm not going to talk about it right now. Well, now I'm going to talk about it. Type 1 error means that you had a situation where the true state of the world was that the null hypothesis was true. Group 1 and group 2 had the exact same mu, or people were on average exactly the same before an event as they were after an event. Or a subsample that you thought might have been different from the population was just the same as the population. All right. If the null is true, but you nevertheless happen to pull a weird sample that gives you the impression that the null hypothesis is false, you'll commit a type 1 error. And it happens. It happens alpha of the time. That's what alpha is. Alpha is the probability we are willing to tolerate that we'll get a significant effect out of a non-significant world. All right. But the opposite, the flip side, the mirror of a type 1 error is a type 2 error, where an effect really does exist. But when you run your study, you get a result that causes you to say, nope, I'm sticking with the null hypothesis. That would also be an error. And it's one that we kind of want to avoid. Let's take a look here. When you run a hypothesis test, there are two things that can happen. You can either reject the null or fail to reject the null. That's the entire process of hypothesis testing. You make a decision at the very end. depending on how your statistic for analysis and its test ratio compare to the critical value, you will either tell the null hypothesis to get lost or say, yep, we're still good. All right. So there's your decision that has one of two outcomes, accept or reject. At the same time, there is the state of the actual world. This is not something that you know. It's not something you can even figure out with your hypothesis test, but it is the actual state that you were looking to investigate and looking to find out. So in that world, the null could either be actually true or the null could be false. And there is a difference. The difference you're looking for actually is there. If you run a hypothesis test and you fail to reject the null, and the null was in fact true, then what you've done is you've achieved a research objective. You've done the right thing. You have stated something about the world that actually turned out to be true. Good for you. That is a result that's circled here in green and has a green arrow associated with it. That would mean you achieved the research objective. So this distribution down here is the null distribution. It is the distribution of results you'd get from a study if the null hypothesis was actually true. So they center around 0 for like an independent samples design. If the null hypothesis is actually true, then the result that you'll get when you subtract x bar sub 1 and x bar sub 2 is typically 0. And the only reason it would stray from 0 is if you have sampling error that separates the two means. But the further away they are from each other, the less likely that result is to be, because it means you get a lot more sampling error than was expected. Okay, so this is a null distribution. It centers around the actual truth, and the further away you get from the truth, the more rare it is that you'll get that result. All right, so if you get a result that is reasonably close to the truth so that you didn't wander into the area of rejection, you're getting a result that is represented by this green arrow. This green arrow is just an example of one such result that you might get. The null was true and you said it was true, good, great. But if the null is true and you get a result that is out here represented by the purple arrow, then you will have made a type 1 error. The null was actually true. You just got a wonky result full of sampling error that was not your fault, but you have caused yourself to reject the null hypothesis because your test ratio was more extreme than the critical value that falls right there. Type 1 error. All right. Here's the other possibility. We've had to introduce another reality. We've had to introduce another curve. That H sub 1 curve, I'm calling that the alternative hypothesis curve. That is the curve that represents the values and frequencies of results you get from your study if a particular prediction about the size of the difference between two groups is actually true. Okay? So in the example that I used way back in the first slides, if this is the curve that you get if the basketball team was just as tall as everybody else, that would center around 0. Okay, if it's true that everybody is basically of equal height, plus or minus some sampling error, no matter whether they play basketball or not, then if you took a sample of regular people and you took a sample of basketball players and you compared the means of those samples, most of the time you'd get something close to 0. But if it was extremely negative in one direction or extremely negative in the other direction, that would be a rare result. However, if some alternative hypothesis was true, and say the reality of the world is that the mu of the population of college basketball players is 3 inches taller than the regular population, then what you would actually be doing when you run a study is pulling a statistic for analysis, an x bar sub 1 minus x bar sub 2, out of this curve, which is offset, shifted, moved from the null hypothesis curve by 3 inches. So the distance between the top of this curve and the top of that curve is 3 inch units, okay? The value of 3 inches. So when you pull a regular group of people and a group of basketball players and you subtract their means, most often you get something that is close to 3. But sometimes you get a bigger difference and sometimes you get a smaller difference. That's because even if 3 inches is the actual truth, any sample that you take around that reality is itself going to bring some sampling error with it, which might cause you to get a different result. Okay, here's where type 2 errors come in. Type 2 errors happen when an alternative hypothesis, like the one I put here, the basketball players are 3 inches taller on average than the normal population, is true. But nevertheless, when you run your study, you end up getting a result that causes you to make the decision to accept the null hypothesis. That is going to happen anytime your statistic for analysis is less extreme than the critical value. That's a type 2 error. The critical value determines what decision you make. And if the decision is wrong and you've accepted the null, then it's a type 2 error. However, if there really is a 3-inch difference between basketball players and the regular average student body population, and you end up getting a result that exceeds the critical value and says, I reject the null, then great, you've done the right thing. You've achieved the research objective. Okay? That is what we're actually after. That's usually where we want to be when we run a study. We think there's something there. We think that there's an effect there. We want to reject the null so that we can declare that our proposed difference thing in the world actually exists. And so we're looking for results that are going to be in this green area. All right. Critical thing to keep in mind. The decision that you make is determined solely by whether your statistic for analysis is on, in this case, this side or this side of the critical value. So let me go back and do that again here. Okay. I'm going to annotate this. Okay. The critical value is the only thing that determines whether or not you're going to reject the null. So if your results are anywhere to this side of the critical value, you're going to accept the null. It doesn't really have anything to do with this curve. It's just like if your results are here or here or here or here or here, you're going to make a decision that causes you to accept the null hypothesis. But if you get a result that is on this side of the critical value, then you're going to make the decision to reject the null hypothesis. So this result, accept the null. This result, reject the null, as well as this one, this one, this one, on and on. You understand? So whether or not you decide to accept or reject the null has everything to do with the critical value. And so therefore, the critical value is what divides the null hypothesis into making the right decision or making a type 1 error. But that same critical value that doesn't change is also the value that splits the alternative hypothesis curve into a correct rejection, the research objective, or type 2 error. They are both criterion, they're both pegged to the same value, the critical value. And remember, you calculate the critical value by taking the null assumptions and figuring out where the critical value should start based on the alpha that you're willing to accept. That means where your alternative hypothesis falls relative to the critical value is not up to you. Okay, it depends on how much error you have, and it depends on how big the difference is between those two distributions. All right, so clear that and move on. All right. We have names for the probabilities associated with making a type 2 error or making a correct rejection of the null hypothesis. The probability of making a type 2 error if an alternative hypothesis is actually true is known as beta. The area of this yellow portion right here is known as beta. The area of the green portion is known as power. Beta and power make up the entirety of all possibilities that you could get if the null hypothesis was true. So since they are proportions of probability, they both add up to 1. All possibilities in the world have to add up to 1 if they are proportions of possibility. All right? So if the alternative hypothesis then turns out to actually be true in the world, you will make the right decision, which is to reject the null 1 minus beta of the time. 1 minus beta is a probability expression. It is also, therefore, an expression of proportion under a curve. Same thing we used to do with the null hypothesis curve. Remember alpha? Alpha was a proportion under the curve. It was also the probability that you would reject the null in error. So proportion and probability have a strong relationship to each other when we're talking about these things here in statistics. So power is the probability of rejecting the null hypothesis if your alternative hypothesis is actually true. The probability of failing to reject the null hypothesis is beta. That's a type 2 error. Again, assuming that the alternative hypothesis is in fact true. This comprehensive summary slide is another thing that I have included in your packets of printed out materials. And if you left it in campus or you don't have it, it's up on the Scholar page. There are so many moving parts that all depend on each other that I had to put them all on one slide in order for you to get an idea about how they relate to each other. So I'm going to start this story here and fill in little parts of what's going on with and under each one of these curves as I move along to show you how everything is part of the same story and fits together. First things that are up on this slide already. I'm going to call this left-hand normal looking curve, this one right here, okay, I'm going to call this the null hypothesis curve. This is a distribution, a frequency distribution of all the results that you would get from your study if the null hypothesis was true. It centers around the actual null value plus or minus sampling error in either direction. This, just like the last slide, is the alternative hypothesis curve. It is a frequency distribution of results that you would get if a particular alternative hypothesis was true. The most common value would be the right answer for the difference between two populations, but again, also plus or minus sampling error. The difference between these is known as the effect or the treatment effect. That is the difference between being a regular person and a basketball player. It could be the difference between taking pain medication or no pain medication as measured on a pain scale. It could be the difference in height between a population of people who does take human growth hormone and a population of people who doesn't take human growth hormone. That would be the treatment effect of human growth hormone is 2.5 inches, okay? So that's the effect of the treatment effect, is how much separates the null assumptions from an alternative hypothesis assumption. All right, now, that right there is the critical value. That is determined by picking 5% or alpha, whatever alpha is, but alpha is usually 5%. That critical value is dropped into the story by figuring out where the most extreme alpha of the null hypothesis curve starts and saying that border, boom, that's critical value. That means everything on the more extreme side is going to cause you to reject the null. If the null is true, that rejection is a type 1 error. It was a mistake. But if the null was not true, if this alternative was in fact true, then going on the other side of that critical value is going to be the mistake. That is going to be known as a type 2 error. Now here's the thing. Did you actually make a type 1 error if you rejected the null? Or did you actually make a type 2 error if you failed to reject the null? you never actually get to know as a researcher. When we talk about type 1 error and we talk about type 2 error, we talk about knowing two different things. The first thing is the decision that you made, and the second thing is the actual objective reality of the infinite populations out there in the world. Well, the reason we have statistics is because we don't actually know what the infinite populations out there in the world actually are. The best that we can do is estimate them using statistics. So here's the problem with research in general, which is this: a type 1 error looks exactly like a correct rejection. If you're in the region of type 1 error, it looks just like you're in the region of power. Okay, and you don't know unless you know the underlying behavior of the populations, which is unknowable. You can't figure out whether you've made a type 1 error or not. So when we discuss these things in class, theoretically, I'm going to be having to throw at you a whole lot of magical assumptions, magical information about whether or not the null hypothesis or alternative hypothesis was actually true out there in the real world. So when I ask you about power, I'm automatically, so that'll help to determine whether or not a type 1 error is power or whether a type 2 error is a correct acceptance of the null hypothesis. The other thing that rolls into this is that knowing which universe you're dealing with, whether the null was true or the alternative is true, is something that I'm going to try to specify as often as possible. But if I don't, and I'm asking you questions that have to do with the proportion of the alternative hypothesis curve, like power or 1 minus power, beta, then I'm automatically talking about an assumption under which the alternative hypothesis is true. If I'm asking you about alpha, I'm automatically assuming that the null hypothesis is true, and we're operating under the null hypothesis curve. All right. To finish up then, I want to talk about a few things that affect power. The first thing that affects power is the size of the treatment effect. A big treatment effect will make it easier for you to get statistically significant results. So a big effect will give you a lot of power, a small effect will give you less power. And here's a little animation to show you how that works. Here are a couple of, here's a null hypothesis curve and an alternative hypothesis curve that are separated by a particular treatment effect. Now look what happens if that treatment effect gets a lot bigger. Oh, now you'll realize that the proportion of this curve that is on the correct side of the critical value has just increased dramatically. Look, it used to be that much. Now that we move that out, instead of being this proportion, it now includes that whole proportion. So the probability of making a type 2 error, which is this chunk right here, has shrunk significantly. So if you have a nice, big, juicy treatment effect, it's a lot easier to find statistically significant results. If you have a very tiny treatment effect, however, it can make finding results quite difficult. Take a look at this one. Here's your null hypothesis curve. Here's your alternative hypothesis curve. You actually have, if your alternative is true, you've got a distance here. You've got a difference between these two curves of this much. But if you ran a study asking if one group is different from another group, and you pulled a result from this alternative hypothesis curve that is the way it is, if your hypothesis is actually true, take a look at this sad state of affairs. Most of the results that you would get, pick a different color here. Most of the results that you would get if your alternative hypothesis is actually true are still going to be results that are on the wrong side of the critical value. That's terrible. Okay, so you might have been right about the effect of your treatment. You might have been right that something is there, but most of the time you're still going to make the wrong decision. The probability of you making the correct decision out here, that is your power, and it's a long shot. Okay, it's about maybe 20% of the curve. So in that case, your power is 0.2. It's even if you're right, you only have a 20% chance of declaring that you're right. So a small effect means that you probably have to go to some special effort to shrink the amount of standard error in order to get a lot of separation between these curves, so that even if you're right, you'll get a result that says that you're going to be right. That gets us to the other things that affect power. Okay, the size of the standard error. There are a couple of ways that you can reduce your standard error. A well-run study will just have less randomness in it, and this reduces the amount of error that you have to deal with. The other thing that you can do to manipulate standard error is to increase the sample size. Okay, so either way you do that, a smaller standard error means that whatever treatment effect you're actually looking at, if you have a small standard error, then that effect is going to represent more of those standard errors. And since since critical values and test ratios are all about counting up the number of standard errors, if your standard error is small, then you're going to get more of them so that you can exceed the critical value more easily. So take a look here. This is what it looks like with a regular amount of standard error. But if you took that standard error and shrunk it, you'd get some separation between those two curves. The critical value would be dragged in with the null hypothesis curve, leaving a whole lot more of the alternative hypothesis on the side of the critical value where you want it. If we could further and further and further get that standard error down, you'd see more and more and more separation between these two possibilities, approaching the point where no matter what you get, as long as your alternative hypothesis is true, you'll end up rejecting the null hypothesis. The last thing that I'm going to talk about is the possibility that you can increase the probability of rejecting the null if you manipulate the alpha level. This is not something that you should do, but it is something mathematically that works. All right, keep in mind, power, the probability that you will reject the null hypothesis if an alternative is true, brings with it the assumption that the alternative is true. So as long as it's true, you just want to make sure to reject the null. Okay, fine. So basically what you want to do is just drop your critical value as low as possible so that no matter what you find, it causes you to reject the null and accept your alternative hypothesis. Because, right, it's true, assuming it's true. But the thing is, increasing your alpha also brings with it an increased probability that if the null is true, you're going to call it false. Here's what it actually looks like. If I beef up the alpha, I am now allowing myself to say, oh, if this null is true, then like 30% of the time I'm going to reject it anyway. But if I'm lucky enough that the null is false, now a whole lot more of that curve has fallen into the correct rejection power area. So it's a trade-off, as it always is. This is an entire field called signal detection. And signal detection is all about managing the probability of a false alarm versus the probability of a hit, which means that you're going to have to deal with a certain amount of probability that you're going to make the wrong call sometimes, or else you're never going to end up making the right call. I think the best way to think about that is in terms of like the justice system. In the justice system, we're very, very, very concerned with making sure that we don't send innocent people to jail, or at the very least, that's how it's supposed to work. And so we have a system that's set up in such a way that if a person is probably guilty, we still set them free unless we're absolutely sure. Now, that means letting a lot of guilty people free, but we're supposed to be comfortable with that because it keeps us from making an error of sending somebody innocent to jail. We don't want to make a false alarm on guilt. And so we miss a lot of actual guilt, okay? So the only way that you could absolutely guarantee that no innocent person ever went to jail would be never to convict anybody. And you'd win. You'd never send an innocent person to jail. You would set your critical value, your criteria value so high, make your alpha so stringent, like move it way out here, that no matter how much guilt somebody had, they never got convicted. All right, fine. But that means that every innocent person who was dragged into court would also go free. Mission accomplished? Probably not. Um, the other thing would be if you took your critical value and you made it very easy to get over, moved it way down here, well, you know what? You'd never miss a conviction. Every guilty person who ever went to trial would go to jail. And the only way to do that would be to send everybody to prison who ever went to trial. You would make sure that you never missed a guilty person. At the same time, every innocent person who went up for trial would also be in prison, which is not something that we tend to think is a good idea here in America. So that is the kind of thing you can think about when you talk about manipulating alpha, which directly manipulates the critical value. It's a trade-off in how much you are interested in making sure that you get every true possibility versus how much you're worried about making a mistake. All right, well, that's about it. We're going to be doing an in-class assignment on Thursday. It is really more of a quiz when it comes to power, and I will share with you a little bit more about how we're going to cover power on the test. But until then, take care, and I'll see you later.